When we think of prehistoric giants, our minds immediately conjure images of towering dinosaurs. Brachiosaurus stretching its neck toward the clouds, or T-Rex thundering across ancient landscapes. It's a perception reinforced throughout our lives, from childhood toys to blockbuster films. However, archaeology has uncovered a surprising truth. A real-life giant elephant once challenged the notion that dinosaurs were the most powerful land animals. Palaeoloxodon walked the Earth until just 40,000 years ago, meaning our own species potentially encountered these colossal creatures. By the end of this video, you'll understand how this elephant achieved such massive proportions and why this evolutionary experiment ultimately failed. Enter Palaeoloxodon paticus, an elephant that would have made even the most intimidating non-sauropod dinosaurs look relatively modest by comparison. Standing at an astonishing 17 feet tall at the shoulder, approximately the height of a basketball hoop plus an entire player standing beneath it. This colossus weighed an estimated 22 tons. Modern African elephants, impressive at 13,000 pounds, represent merely a quarter of this ancient giant's mass, with each footstep leaving depressions deep enough to become small ponds after rainfall. When paleontologists first unearthed the fragmentary remains of this species, their reactions bordered on disbelief. The femur bones alone exceeded anything previously documented in the mammalian fossil record, surpassing even those of the mighty Triceratops. These extraordinarily dense leg bones immediately suggested something exceptional in mammalian evolution. Initial skepticism led to rigorous scientific validation. The 2023 study became particularly significant when researchers examining a more complete specimen, identified as CF Palaeoloxodon pneumaticus, provided crucial confirmation. This related elephant species was estimated at 18 to 19 tons, still colossal, lending credibility to the Palaeoloxodon paticus measurements. The same study examined Paraceratherium, previously considered the largest land mammal, assigning it a weight of approximately 17 tons, effectively confirming Palaeoloxodon paticus as the pinnacle of mammalian terrestrial size. What differentiates this elephant from other prehistoric giants is its sheer mass. While some dinosaurs reached comparable or greater heights, particularly sauropods, Palaeoloxodon paticus outweighed every non-sauropod dinosaur ever documented. Even Tyrannosaurus rex, at approximately 8 to 10 tons, would have been less than half this prodigious proboscidean's mass. Multiple complementary approaches convinced scientists of this elephant's superlative status. Comparative anatomy with extant elephants, mathematical modeling of skeletal proportions, volumetric displacement calculations, and cross-referencing with other giant mammals. This convergence of methodologies created a compelling scientific consensus. This discovery challenges our assumptions about evolutionary trajectories. Rather than existing in the distant past, Palaeoloxodon paticus reached its enormous proportions relatively recently in geological terms, during the Middle to Late Pleistocene, hundreds of thousands rather than millions of years ago. This evolutionary anomaly raises a fascinating question. How did Palaeoloxodon paticus overcome the biological limitations that should have constrained its growth? Its existence defies conventional understanding of mammalian biology, with adaptations that transformed it into a living colossus. Picture a giraffe, the tallest animal alive today, stretching its neck to its maximum height, only to find itself completely overshadowed by this prehistoric elephant, whose massive shoulder would rise significantly higher than the giraffe's uppermost reach. The evolutionary pressures driving this extraordinary growth involved a complex interplay of factors. Resource competition favored larger individuals who could access foliage beyond other herbivores' reach. Predator avoidance played a crucial role. Even juvenile specimens would have intimidated all but the most desperate carnivores. Pleistocene climate conditions favored larger body mass, as thermal efficiency helped these giants maintain stable temperatures despite environmental fluctuations. Evolutionary advantages create engineering challenges. The square cube law presents a fundamental problem. As an organism grows, its mass increases as a cube of its dimensions, while structural strength increases only as a square. Palaeoloxodon paticus needed revolutionary biological engineering to overcome these constraints. Like a suspension bridge requiring exponentially stronger cables as its span increases. Its specialized skull structure featured a prominent crest that anchored powerful splenius muscles. This cranial architecture represented a sophisticated weight-bearing system, enabling the elephant to support its massive head with precision. The crest varied in size depending on growth stage and gender, becoming most pronounced in mature males. The elephant's tusks, reaching an astonishing 4 meters in length, represented another biological engineering marvel. The reinforced skull with robust muscle attachments allowed Palaeoloxodon to wield these enormous structures effectively without destabilizing its frame. Its unique head design enabled lowering close to the ground without losing balance, critical for consuming enormous quantities of vegetation daily. This mechanism, combined with specialized leg bones engineered to support tremendous weight, created a biological skyscraper. These anatomical innovations transformed Palaeoloxodon paticus into an integrated system of counterbalances and reinforced structures that defied physical constraints. Each skeletal element was precisely calibrated to distribute its tremendous mass. While Tyrannosaurus rex has dominated our collective imagination as the ultimate prehistoric terror, the statistics tell a surprising story about which animal might actually dominate in a confrontation that evolution never allowed to happen. Imagine these titans facing off across a Pleistocene plain. A 12 to 13 foot tall T-Rex weighing 8 to 10 tons, squaring up against the towering frame of Palaeoloxodon paticus. The elephant outweighs its dinosaurian counterpart by a factor of at least 2. Would raw power or sheer mass win the ultimate prehistoric battle? T-Rex's primary weapon was undoubtedly its devastating bite. Paleontological research indicates the tyrant lizard possessed a bite force estimated to be among the strongest of any terrestrial animal, capable of crushing bone and tearing through flesh with ease. This adaptation made it an apex predator, allowing it to effectively hunt and dispatch large prey within its ecosystem. But how would this compare to Palaeoloxodon's defenses? The prehistoric elephant possessed skin likely an inch thick, a natural armor providing significant protection against even the most powerful bites. Combined with its enormous tusks, which could be wielded as lethal weapons, the elephant had both defensive and offensive capabilities that would give any predator pause. What happens when unstoppable force meets immovable object? The confrontation would be further complicated by behavioral factors. Evidence suggests Palaeoloxodon species lived in complex herds, offering enhanced protection. This social structure meant that a predator would face potentially several opponents working in coordinated defense. T-Rex, while possibly engaging in some social behavior, primarily relied on individual hunting prowess. Speed and mobility would also play crucial roles. Modern African elephants can charge at up to 25 miles per hour. T-Rex was estimated at 12 to 25 miles per hour, potentially giving it a slight agility advantage. However, The sheer momentum of a charging Palaeoloxodon would have been virtually unstoppable once in motion. Each of these animals dominated their respective eras. T-Rex evolved as a specialized predator in an ecosystem with massive herbivores like Triceratops. Similarly, Palaeoloxodon paticus's extreme size provided advantages against the predators it actually encountered. Of course, these species were separated by over 30 million years. T-Rex from the late Cretaceous period, and Palaeoloxodon from the much later Pleistocene epoch. They inhabited entirely different worlds, making this matchup purely hypothetical, yet fascinating to contemplate. The adaptations that made Palaeoloxodon paticus thrive reveal a counterintuitive truth about evolutionary success. Sometimes bigger truly is better, despite what biological constraints might suggest. In the delicate balance of natural selection, this prehistoric elephant pushed the boundaries of terrestrial size to their absolute limit, creating a magnificent paradox of adaptation that both ensured its survival and ultimately contributed to its downfall. Evolution favors extreme traits only when advantages offset their costs. Palaeoloxodon paticus maintained colossal proportions at an extraordinary metabolic cost, approximately 150,000 calories daily, equivalent to running 60 modern refrigerators simultaneously. This immense demand meant constant foraging, with individuals spending most waking hours consuming vegetation to sustain their massive frames. The Middle Pleistocene epoch, 781,000 to 126,000 years ago, provided ideal conditions for these giants with its diverse vegetation patterns, particularly extensive grasslands. These feeding grounds supplied the abundant low-level vegetation necessary to fuel bodies of such magnitude, creating a perfect ecological niche for megaherbivores. The evolutionary trade-offs of gigantism were balanced by clear advantages. Predator resistance. Their imposing stature made them virtually impervious to all but the most determined pack hunters. Competitive advantage? Accessing food sources beyond the reach of smaller herbivores. Thermal efficiency. Lower surface-to-volume ratio buffered against temperature fluctuations. Social complexity. Herd structures enhanced protection and resource location. Yet these specialized adaptations carried inherent vulnerabilities. Extreme caloric requirements became potentially fatal when resources diminished. Specialized skeletal structures limited mobility in certain terrains. Long maturation periods and low reproductive rates left populations vulnerable to rapid environmental shifts. The social structure of these behemoths reinforced their evolutionary success. Fossil evidence suggests Palaeoloxodon species lived in complex herds similar to modern elephants, providing additional protection for vulnerable members and enhancing their collective ability to locate food sources and defend against threats. This social intelligence, combined with their physical dominance, created a remarkably successful strategy that persisted for hundreds of thousands of years. What makes Palaeoloxodon paticus so compelling is that its extreme specialization, the very adaptations that made it successful, became its greatest vulnerability. The massive caloric requirements, sustainable in resource-rich environments, became liabilities when conditions changed. For all these biological costs, evolutionary pressure clearly favored the benefits of extreme size in this lineage. The ability to overcome predators, reach otherwise inaccessible food sources, efficiently regulate body temperature, and maintain complex social structures collectively created an evolutionary niche. These animals dominated for far longer than our own species has existed. The evolutionary arms race that produced the remarkable Palaeoloxodon ultimately met its match not in bigger predators or climate catastrophe, but in creatures barely reaching a fraction of their size. Archaeological sites across Europe and Asia tell a remarkable story. Human bones and tools frequently appear alongside the remains of these colossal elephants. This physical evidence confirms what seems biologically improbable. Early humans not only shared landscapes with these titans, but actively hunted them. Homo heidelbergensis and later Neanderthals occupied the same temporal and geographical spaces as these massive pachyderms. At just 5 to 6 feet tall against an animal standing 4 times their height, these human ancestors faced odds comparable to modern humans, hunting blue whales with hand tools. Yet they succeeded where larger predators failed. The archaeological evidence tells this improbable story through butchering marks etched into Palaeoloxodon bones, precise patterns revealing how humans methodically processed these enormous carcasses. Specialized tools found alongside these remains confirm deliberate hunting rather than opportunistic scavenging. Imagine the tension as a small band of hunters approached a creature that could end their lives with a single misstep, their spears seemingly insignificant against the elephant's massive frame. Human ingenuity and social cooperation made the impossible possible. Early humans developed specialized projectile weapons and hunted collectively, using sophisticated coordination to overcome their physical limitations. Rather than confronting these giants directly, hunters likely employed ambush tactics, using environmental features like mud pits or ravines as natural traps. Picture the careful planning as hunters studied elephant movements, waiting for vulnerable individuals to separate from the herd before launching their coordinated attack. These hunting strategies marked a fundamental shift in predator-prey dynamics, where cognitive adaptations, planning, tool-making, and cooperation created an entirely new kind of predator. The elephant's massive size became a liability against hunters who could track them for days, waiting for moments of vulnerability. The meticulous butchering patterns revealed the extraordinary value these animals represented. Every part was utilized. Meat fed dozens for weeks, while tusks and bones became raw materials for tools and shelters. The immense risk involved suggests these weren't merely convenient food sources, but critical resources influencing settlement patterns and social organization. As human hunting technology grew more sophisticated, pressure on Palaeoloxodon populations intensified. Combined with changing climate patterns, these giants found themselves caught between diminishing habitat and a predator uniquely equipped to exploit their vulnerabilities. The triumph of brain over brawn represented a fundamental shift in Earth's evolutionary trajectory, one that would ultimately reshape every ecosystem on the planet. The extinction of Palaeoloxodon paticus represents one of paleontology's most complex puzzles. Around 40,000 to 50,000 years ago, these magnificent creatures vanished during the late Pleistocene, a period marked by dramatic environmental flux. Fluctuating temperatures and altered precipitation patterns fundamentally changed the ecological landscape, causing expansive grasslands to shrink and fragment as glacial advances and retreats reshaped continents. This cooling climate triggered a cascade of environmental changes that proved catastrophic for specialized megafauna. Their immense size, specific dietary requirements, and specialized anatomical features transformed into fatal vulnerabilities. Those massive frames, previously advantageous for dominating landscapes and resisting predation, now demanded unsustainable nutrition from increasingly scarce resources. Fossil evidence reveals a telling pattern. Palaeoloxodon populations gradually contracted in territory and declined in numbers rather than disappearing simultaneously. This geographical restriction created isolated groups that could no longer migrate to favorable habitats, leaving them vulnerable to localized environmental pressures and heightened competition for dwindling resources. Significantly, this population contraction coincided with human expansion and technological advancement across the same territories. The archaeological record documents early human populations expanding their range and refining their tools precisely when Palaeoloxodon faced its greatest challenges. The extinction narrative emerges as a perfect storm of pressures. Climate change reduced available food sources while simultaneously making the elephants more vulnerable to hunting as they congregated around remaining viable habitats. Neither factor alone may have eradicated these formidable creatures, but together they sealed their fate. Today's African and Asian elephants represent merely a shadow of the once diverse Proboscidean family. Modern genetic research reveals fascinating connections. The African forest elephant, Loxodonta cyclotis, shares closer genetic ties with Palaeoloxodon than with the African bush elephant, highlighting their complex evolutionary history. The demise of the largest land mammal that ever lived reflects not a single catastrophic event, but a complex interplay of environmental changes and human activity. A sobering tale where specialized adaptations became evolutionary dead ends in a rapidly changing world. The extinction of Palaeoloxodon paticus serves as a poignant reflection on evolutionary adaptation itself, a magnificent testament to what natural selection can achieve, yet ultimately constrained by its own specialization. This colossal creature pushed the biological boundaries of terrestrial size, only to find those same adaptations becoming vulnerabilities when environments shifted. Today, the African forest elephant, genetically closer to Palaeoloxodon than their bush elephant cousins, faces these same challenges. As habitat fragments and humans encroach, these living connections to Earth's megafaunal past mirror their ancestors' final struggles. Will we recognize this evolutionary echo before it's too late? Their conservation safeguards not merely a species, but our connection to a vanished world of giants.